different frequency bands and 3 different amplitudes. The frequency characteristics of the noise were as follows. We used the 50 to 150 hertz that we assumed would interfere with the dominant frequency of the male calling song. Next, the 50 to 500 hertz that would interfere with the harmonics as well, because they can be quite important. And then the 500 to 1000 hertz noise, which we assumed would be outside of the spectral range of the female calling songs. The amplitudes that we use were -6, 0, and +6 decibels relative to the female calling song at the branching point of the stem, because this is where the male made his directional decision. The plants all had similar dimensions, and we changed them every second day to reduce the effect of pheromones left on the plant by the previous males. And during the experiments, we were recording the vibrations with 2 laser Doppler vibrometers and animal movements with a digital video camera. Altogether, the males were tested with 10 different treatments in a paired treatment design, and we used a total of 30 males in the behavioral experiment. It was randomized by day and by treatment. So after being carefully placed on the top of the plant, the males had 15 minutes to localize the origin of the female calling song that was, as I said, transmitted either to the left or the right leaf. If the males didn't localize the source after 15 minutes, we terminated the experiment, same as if the animal left the plant. And we started timing them at the moment when they produced their first courtship song or started moving, as we assumed that all of the movements were considered searching movements. We have measured the amplitude of the female calling songs on all of the noises on these 16 positions on the plant that you see on the slide. The positions are on the x-axis and the relative amplitudes are on the y-axis. The blue and red bars represent 95% confidence intervals of the calling song amplitude, 95% confidence intervals of the calling song amplitude averages for 6 different plants. And the 3 black bars that are present on each position represent means and standard errors of 3 different amplitude levels of the, in this case, 50 to 150 hertz noise. From left to right, they go -6 decibels, 0, and +6 decibels, relative, of course, to the female calling song measured at the branching point. We can see that the amplitude of the noise was much lower than the calling song amplitude on both the left and the right leaf, but in the middle section on the stem and the leaf petioles, the noise was equal or slightly larger than the female signal. And the same can be said also for the 50 to 500 hertz noise. Notice how the black bars change. And for the 500 to 1000 hertz noise, this basically means that the most problematic areas for the males on the plants in terms of the signal to noise ratio were on the stems and the petioles, but not so on the leaves. If the animal had gotten to the leaf, we assumed that it would find the vibrational source, but that wasn't always true. And now for some of the results. On the top left chart, you can see the percentage of signaling animals for each treatment. In the green, we have the control treatment without noise. In blue, we have the 50 to 150 hertz noise for all 3 different amplitudes. In the purple, we have the 50 to 500 hertz noise. And in the brown, the high frequency 500 to 1000 hertz noise. We can see that in the control treatment, all of the animals were signaling, while in noise, the signaling was reduced in the low and the low-medium noise treatments, while in the high-frequency treatments, it was very similar to the control treatments. A similar result can be seen on the top right and the top left charts. The upper one represents total signaling time, and the bottom one, the duty cycle, which is basically total singing divided by the total And we can see that the most disruptive noise treatments were again in the low frequency bands, specifically the 50 to 500 hertz noise that covered, as we remember, the frequencies, the dominant frequencies and the harmonics as well. Again, the treatments with the high frequency noise were less problematic for the animals in the terms of signaling behavior. But on the bottom left, the last chart for the signaling, we can see the latency of the first signal at the start of the experiment, and the latency was larger in all noise treatments compared to the control, but animals had the hardest time starting to signal in the high amplitude, low frequency noise seen here. Next, we have the searching behavior and localization of the two sources of vibrations. On the upper left chart, we can see that there was no difference between treatments in terms of percentage of searching animals. However, on the right, we can see that in terms of total searching, we can again see that the low frequency noise had influenced the behavior more than the high frequency noise. On the bottom chart, we have the percentage of animals that localize the source of vibrations. And we can see that for all noise treatments, the searching behavior was basically lower than in the control treatments, which is interesting because the signaling and searching behavior, as we've seen, was not that much hindered in the high noise treatments, but they still can't localize the source of the vibrations for some reason. And now lastly, I want to talk a bit about the neurophysiological part of the experiment. So we have used similar stimulation like the one in the behavioral experiment to test the response of vibrational receptors in the legs. The animals were sedated by being placed in the fridge for 5 minutes, and then we have removed the muscles and the organs so that the ganglia were exposed, and we could access the leg nerves from the dorsal side of the animal. Then we have used suction electrodes to measure the somatic extracellular potentials from the leg nerves, and the legs were fixed to the mini shaker and stimulated with female calling songs and different noise combinations. For the stimulation protocol, we have used the same bandpass noises, but we have expanded the amplitude range from -24 decibels to 0 decibels. They are represented here on the x-axis. Each female calling song and noise combination included 10 female signals, and the total stimulation length for each amplitude was around 60 seconds. The amplitude of the female calling song was 1 millimeter per second, which is in the natural ranges of the female calling song on the plant. After measuring the response, we sorted the action potentials that we got and measured the instantaneous frequency rate of spikes, as you can see on this uppermost trace. We can observe that the responses to individual female calling songs can be seen very clearly without the background noise. But as the noise gets louder, as it gains in amplitude, the response to female signals gets blurred. To see it more clearly, we have charted the average spike rates as peristimulus time histograms, and on the y-axis we have different frequency bands of noise, and on the x-axis we have the amplitudes of noise increasing from left to right. And then in gray, we have the binned average frequency response of the 10 female signals, and we can see that the frequency of spikes is always much higher during the presentation of the female signal than it is in the surrounding noise. But as the noise gets louder, again, the receptors in the legs increase their action potential generation, especially in the 50 to 150 hertz noise, and in the 50 to 500 hertz noise, but not really in the 500 to 1000 hertz noise. Therefore, we could assume that the high frequency noise doesn't disturb the animals as much as the low frequency noise, and we saw that this was indeed true for both the signaling and the searching behavior, but not so for the localization behavior on the plant. And therefore, we assume that even though the frequency of action potentials in the high frequency noise remains plus minus the same as in the control, the noise still somehow affects the timing of the action potentials, which guides the localization behavior. So this is it for me for now, and I will be happy to take any of your questions.